morning, everyone. I'm from Microsoft, and I'm thrilled to be here at Conf42. Network engineering, as many of has traditionally been about cables, routers, and keeping systems online. But today, that world is being completely redefined. We're entering an era where AI isn't supporting just the network, it's actively running it, optimizing performance, predicting failures, and adapting on the fly. In this talk, we'll explore how AI is reshaping network engineering, what new skills we need, and how we can design scalable, reliable, and intelligent networks for this AI-driven future. Let's start with how our has evolved. The traditional approach was straightforward: manually configure devices, monitor uptime, and react to problems when something broke. If your router failed at 2 a.m., someone got a call. Today, we have shifted to a modern paradigm where intelligent systems can predict issues before they occur, optimize themselves, and make decisions based on data. For instance, modern data centers can now automatically reconfigure traffic patterns or in the paths basically when latency is noticed on a particular path with no human in the loop. So the role of network engineer has changed from being an operator to becoming a systems architect and a data-driven strategist. Network engineers now span three worlds: enterprise networks, cloud providers, and telecom operators. Enterprises care most about compliance, uptime, and security. Think of a global bank that must follow strict regulations that keep trading systems live 24/7. Cloud providers emphasize automation and elasticity. Companies like Microsoft Azure or AWS need networks that scale across continents automatically. Telecom operators handle massive traffic and carry great reliability. Imagine using billions of IoT connections simultaneously. Each network is unique, yet they are deeply interconnected. The future engineer must be fluent in all these three. In enterprise environments, the challenge is balancing reliability and regulation. Networks must meet audit, data sovereignty, and zero trust requirements while staying efficient. For example, a healthcare company integrating patient data across multiple clouds must ensure HIPAA compliance without slowing access to doctors. Engineers have to design architectures that maintain redundancy, security, and performance, all while supporting legacy systems that were never meant to talk to modern cloud services. It's like renovating an old house while keeping the lights on. You can't afford downtime. In cloud and service provider spaces, speed and scale is everything. Four imperatives that define these environments is automation. Tools like Terraform or Ansible replace manual configuration. You can deploy hundreds of routers with a single script. Orchestration at scale. Managing thousands of network nodes requires systems like Kubernetes for networking to maintain consistency and reliability. Performance optimization. Sub-second latency can be make or break applications like online gaming, stock trading. Elastic scaling. Networks must expand and contract based on demand. Think of video streaming, traffic during a major sports event. AI ties these together, helping us make real-time data-driven adjustments. Now let's ground ourselves in the core skills that still matter. AI can optimize configurations, but it can't replace deep understanding of routing protocols like BGP, OSPF, and MPLS. For example, when AI recommends a route change, engineers must interpret why. Is it improving latency or masking an underlying topology issue? Likewise, IPv6 security and observability are becoming fundamental. With billions of IoT devices joining networks, IPv4 is simply not enough. So while AI helps automate and enhance, our foundational knowledge remains. The network engineer of tomorrow is a hybrid, part network architect, part software developer, part data analyst. Beyond protocol mastery, we need programming fluency, AI literacy, and data interpretation skills. For instance, when AI models suggest optimizing bandwidth based on telemetry data, you should understand how that model learned. what features it used, and what biases might exist. The more we understand AI, the better we can collaborate with it, turning the engineer into an AI copilot, not a spectator. The toolbox of a modern engineer looks very different now. We are seeing tools like Ansible, Norner, Terraform, NetMiko, and Napalm, all focused on automating repetitive tasks. If you add Python, YAML, JSON, and JIT, this is now the new command line. Picture this. Instead of configuring one switch at a time, you push a git commit and the change deploys across hundreds of devices with validation checks built in. That's why the new baseline is clear. Python, Git, Ansible, APIs, and SDN controllers. These are the keys to building intelligent, scalable systems. AI is already deeply embedded in network operations. It helps with anomaly detection, spotting unusual spikes in traffic that might signal an predictive maintenance, identifying ports or links likely to fail soon, root cause analysis, correlating thousands of logs in seconds to find the issue. Without AI, these tasks will become humongous and take a lot of time. But with the help of AI, we're able to scale up much better and root cause it much more efficiently. A real world example is a global telco used an AI to detect Wi Fi degradation across regions before customers ever noticed, saving millions in support calls. These capabilities transform operations from reactive to proactive, from firefighting to forecasting. The shift AI brings is not incremental, it's transformational. Tasks that took hours, like sifting through telemetry data, now happen continuously and automatically. AI systems analyze traffic behavior, link health, and security patterns to adjust configurations in real time. Imagine a network that knows peak hours for your app, pre-allocates bandwidth, and tunes quality of service parameters before congestion actually happens. That's the power of moving from monitor and react to anticipate and adapt. Self-optimizing networks are where AI truly shines. These are systems that can self-diagnose, zero out traffic around failures, and even heal themselves automatically. For instance, if a link in Singapore fails and the network could reroute to Tokyo in milliseconds without anyone touching a console, the impact is massive: reduced downtime, faster resolution, and lower costs. But autonomy must come with guardrails. Engineers must define safety limits, like what an AI can change, to avoid any unintended consequences. So, this definition of guardrails and how you put safety checks in place is pretty important. And this brings us to a critical truth. AI can enhance but not replace human expertise. AI lacks context. It doesn't understand business goals, regulations, or organization culture. For example, an AI might flag a large data transfer as a security threat, but a human knows it's a sanctioned quarterly backup. The best networks come from AI plus human collaboration. AI accelerates analysis. Humans provide judgment, strategy, and ethical oversight. As engineers, we remain the interpreters and architects behind the intelligence. Future-ready networks are modular, API-driven, and observable by design. API-first design allows systems to integrate and automate easily. Microservices architecture ensures scalability. You can upgrade one service without taking the entire system down. Declarative configuration lets you describe the desired state instead of typing imperative commands. The system figures out how to get there. Observability by default gives AI the data it needs to learn and improve. Think of it as moving from a static machine to a living, evolving organism. Scalability and resiliency aren't add-ons. They must be baked into the architecture. Horizontal scaling adds more nodes, not bigger ones. Stateless design reduces dependencies. Graceful degradation: if one part fails, the system still runs, even if partially. Chaos engineering: deliberately breaking things in testing to build confidence and recovery. And Netflix popularized this idea. Their Chaos Monkey tool randomly shuts down systems to test resiliency. Networks need the same philosophy: plan for failure and design for recovery. So, how do we get there? Here's a 5 step roadmap. Assess current state. Identify where AI can help and what skills your team lacks. Build the foundation. Automate repetitive tasks and connect telemetry. Pilot AI solutions. Try AI in low risk areas like anomaly detection. Scale intelligently, which is like bringing successful pilots into production, monitor results, and refine them, iterate over them. Foster innovation. Encourage learning, hackathons, and cross team collaboration. This journey is iterative. Each phase strengthens the next. It's evolution, not revolution. To wrap up, master the fundamentals. Deep protocol knowledge never goes out of style. Embrace continuous learning. AI and automation evolve quickly. Stay curious. Think architecturally. Design for adaptability and scale from day one. Collaborate across disciplines. The best results come from networking, software, and data teams working together. The future of network engineering isn't about replacing people with AI, it's about augmenting our intelligence, creating systems that learn, adapt, and evolve alongside us. Thank you all, and I hope this inspires you to start building tomorrow's networks today. Thank you.